As the Eastern Roman Empire entered a time of resurgence in the 6th century CE, under the rule of the Emperor Justinian, the dominant philosophical position of the empire was that of Neoplatonism. With its emphasis on a better world of perfect forms, the writings of Plato had found broad acceptance within Christian theology. With this acceptance came an issue that couldn't be ignored. Plato's dialogues had to be integrated, at least to a degree, with the ideas of that other great Greek philosopher, Aristotle, who claimed that the world found in one's senses was all the reality there was. Among those who sought to bring together the two schools of philosophical thought was a man by the name of Simplicius, who wrote incisive commentaries on the works of a number of Greek philosophers from the dawn of the Hellenistic age to the Greco-Roman period of antiquity. His goal was to show that Aristotle's work provided a more deep and fundamental way to understand the truth of Plato, that Aristotle's empiricism could find a place in Plato's cave. One of Simplicius's most influential works was a commentary on Aristotle's great treatise on the nature of heaven, known as De Kaleo. In his commentary, as part of the introduction, Simplicius cited the work of another writer to give context to what Aristotle was saying for a reader who might not understand the distinction between physics and astronomy and the tools that each required. The writer he quoted, one Geminus, had written his own commentary on Poseidonus's meteorology in around 50 CE, where he attempted to enunciate this distinction between astronomy and physics in describing the motions of the heavens. While Geminus's full commentary is lost, we do have the part on the distinction between the two areas of inquiry preserved in Simplicius's introduction. Such are the labyrinthian paths of textual preservation from the times of antiquity until now. So in the words of Geminus, then, we have the following, quote, "It is the task of physical speculation to inquire into the nature of heaven and the stars, their power and quality, their origin and destruction, and, indeed, it can even make demonstrations concerning their size, form, and arrangement. Astronomy does not attempt to speak of any such thing, but demonstrates the arrangement of the heaven, presenting the heaven as an orderly whole, and speaks of shapes, sizes, and distance, of the earth, sun, and moon, of eclipses and conjunctions of the stars, and of the quality and quantity of their motions. Therefore, since it deals with the investigation into quantity, magnitude, and quality in relation to form, naturally it needed arithmetic and geometry. And concerning these things, the only ones of which it undertook to give an account, astronomy has the capacity to make demonstrations by means of arithmetic and geometry. Now, in many cases, the astronomer and the physicist will propose to demonstrate the same point, such as that the sun is large or that the earth is spherical, but they will not proceed by the same paths. The physicist will prove each point from considerations of essence or inherent power, or from its being better to have things thus, or from origin and change. But the astronomer will prove them from the properties of figures and magnitudes, or from the amount of motion and the time appropriate to it. Again, the physicist will often reach the cause by looking to creative force, but the astronomer, when he makes demonstrations from external circumstances, is not competent to perceive the cause, as when, for example, he makes the earth and the stars spherical. Sometimes he does not even desire to take up the cause, as when he discourses about an eclipse, but at other times he invents by way of hypothesis and grants certain devices, by the assumption of which the phenomena will be saved. For example, why do the sun, moon, and planets appear to move irregularly? The astronomer would answer that if we assume their circles are eccentric or that the stars go around on an epicycle, their apparent irregularity will be saved. And it will be necessary to go further and examine in how many ways it is possible for these phenomena to be brought about so that the treatment of the planets may fit the causal explanation, which is in accord with acceptable method. And thus a certain person, Heraclides Ponticus, coming forward, says that even if the earth moves in a certain way and the sun is in a certain way at rest, the apparent irregularity with regard to the sun can be saved. For it is certainly not for the astronomer to know what is by nature at rest and what sort of bodies are given to movement. Rather, introducing hypotheses that certain bodies are at rest and others are moving, he inquires to which hypotheses the phenomena in heaven will correspond. But he must take from the physicist the first principles, that the motions of the stars are simple, uniform, and orderly, from which he will demonstrate that the motions of them all are circular, some moving round on parallel circles, some on oblique ones." Unquote. In this one quotation, as long as it is, we find summed up the entirety of over 500 years of Hellenistic thought, beginning in Miletus and Samos, consolidated in Athens, and then alloyed, recast, and reformed with the ideas of Mesopotamia in the crucible of Alexandria. In this episode, we'll look at the first part of what may be the greatest intellectual achievement of the classical world, a description of humanity's place in the cosmos based on both empirical data and rational thought. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 6, The Geometer's Universe. When we look at the arc of Greek astronomy, it is surprising to see that it began with such humble roots. Compared to the work of other cultures that we've discussed, the earliest astronomical musings of the people of the Peloponnese are parochial, to say the least. There are no great narrative arcs centered around death and resurrection connected to the cycles of the heavens. No mandates from a heavenly supernal lord who might suggest regime change through planetary alignment. No massive structures or astronomical temples, and certainly no libraries with centuries of clay tablets holding the record of each day's observations of the sun, moon, stars, and planets. No, the Greeks were a fractured people who prized personal liberty and independent action over the organizing impulse of empire. As such, each city-state developed its own calendar, each with unique New Year's and month names. The festivals of one town differed from those of another so much that it was hailed as a huge accomplishment when the various poli agreed that they could come together once every 4 years to stage a joint celebration of their shared culture through athletic and artistic contests. Ever contentious, the Greeks jealously guarded their own liberties while seeking to meddle in the affairs of their neighbors, thus pulling their focus to matters of politics and warfare and away from the more astronomical pursuits. This is not to say that the Greeks were entirely indifferent to the sky. As with all cultures, knowing the seasons was essential for an agricultural civilization to be successful, and it was the cycles of the heavens that provided a way to know when to plant and to harvest. However, unlike the cultures around them where the information became tied up in the religious narratives of the civilizations, the Greeks kept their astronomy firmly tied to the earth and the people who worked it. Our earliest records of Greek astronomy were found in the works of Hesiod and Homer. In Homer's epic work on the Trojan War, we find references to the constellations and the descriptions of the shield of Achilles, Orion, the Bear, and the Pleiades, each representing an attitude or attribute of the hero's greatness in the art and conduct of war. Diomedes' armor is compared to that of the star Sirius, blazing forth on the battlefield. Quote, "That star of the waning summer, who beyond all stars rises, bathed in ocean's stream, to glitter in brilliance." Unquote. Here we see the earliest Greek cosmology, that of the earth as a great disk or shield laid flat on the great Titan ocean, who surrounds it on all sides. Above is the solid sky, made of bronze, across which travels the chariot of the sun. Sirius is a star of some ill omen, for as Homer writes, quote, "The star they gave the name of Orion's dog, which is brightest among the stars, and yet is wrought as a sign of evil and brings on the great fever for unfortunate mortals." Unquote. The Heliacal rising of Sirius meant the coming of the summer heat, when, as Hesiod puts it, the desire of women grows just as that of men fades. It is Hesiod who gives us our earliest understanding of the astronomical knowledge of the Greeks in his poem Works and Days. In it, one finds the earliest of the Greek star calendars, or parapegma. These star calendars are lists of the risings and settings of the various bright stars and recognizable constellations so as to mark out the passage of the year. Most of these are correlated to the rising and setting of the sun and are very much like the sayings of the Babylonian Mulapin. For example, Hesiod writes, quote, "When the Pleiades, daughters of Atlas, are rising, begin the harvest, the plowing when they set." This instruction refers to the harvesting and planting of what we know as winter wheat, taken up in early May, just as the Pleiades are rising just before the sun, and then next planted in the cooling weather of late October, when the Pleiades are setting on the western horizon just before the sun comes up in the east. In another passage, Hesiod writes, quote, "When Zeus has finished 60 wintry days after the solstice, then the star Arcturus leaves the holy stream of ocean and first rises brilliant at dusk. After him, the shrilly wailing daughter of Pandion, the swallow, appears to men when spring is just beginning. Before she comes, prune the vines, for it is best so. But when the house carrier climbs up the plants from the earth to escape the Pleiades, then it is no longer the season for digging vineyards, but wet your sickles and rouse up your slaves." Unquote. In this, we have a way of dating Hesiod's work, as it allows us to set the date of the winter solstice as being 60 days before the dusk rising of the bright star in the constellation of Butes, Arcturus. This detail allows us to estimate that the star calendar Hesiod was using would have been accurate at around 650 BCE. Note, too, his intermingling of the seasonal events of the world, i.e. the migration of swallows and the behavior of snails, with the astronomical to fill out his almanac. As far as the calendar went, for Hesiod, the month was 30 days long and was divided into 3 10-day periods. The first for the waxing of the moon, the second for the mid-month, and finally the last for the moon's waning. In each month there were days that were lucky, such as the 8th and 9th days of the waxing decade, and there were others that were less so, such as the Ides, or middle of the month, as Julius Caesar, another man who set forth a calendar, would one day learn. It was through star calendars such as this that the various city-states could find a way to communicate. Rather than having to standardize the various calendrical markers, each could retain their distinct festivals and New Year's dates while being able to set the common events with other polities by referencing the rising of this star at dawn or the setting of another. It is in this tradition of literary astronomy that we find many of the poets and playwrights engaging in philosophical communication. Perhaps the most popular of these is a work by a man called Herodotus of Solus, known as the Phenomena. Written in the 3rd century BCE, this work was second in popularity only to that of Homer, and was translated into Latin on at least 3 different occasions. It was based on the astronomical works of a man we will have occasion to spend a bit of time with later on in the episode, Eudoxus of Callipus, who wrote extensively on mathematical astronomy. Herodotus' Phenomena provided an easy-to-understand compilation of the practical astronomical knowledge of the time, as well as a description of the cosmological models of the day based on the idea of a celestial sphere. It is useful to note also that by the time of Herodotus' writing, it is clear that the Greek writers are well on their way to adopting the Babylonian alignment of gods to the planets, with Zeus taking the place and role of Marduk and setting out and ordering the heavens and its accompanying calendar. As we will see, this adopting of Babylonian knowledge will be a common theme for the Greeks, who excelled at taking the ideas of their neighbors and incorporating them into their way of understanding the natural world as suited them. Even as the Greek literary tradition sought to communicate the knowledge of the astronomers, much as popular scientific magazines do today, there were other threads of work that were beginning to stir in the 5th and 4th centuries BCE, those of the natural philosophers and the mathematicians. We discussed the work of the Greek philosophers from Thales to Aristotle in our series on the history of the atom, but did so in reference to that specific topic. While I would encourage you to go back and listen to those episodes if you'd like to get a better sense of their ideas there, I would like to spend a little bit of time here discussing what they thought about the makeup of the universe, as I think it has great relevance to the picture we will be building. The first figure of Greek natural philosophy is always Thales. While we do not have any writings directly attributed to him, we do have the writings of other philosophers who claim to quote from his work. In these fragments, we find that Thales believed that the universe consisted of a disk-like earth floating in and surrounded on all sides by water, much as Homer portrayed in his writings. This connects with his belief that the fundamental substance of all creation, or element as he referred to it, was water. His reasoning for this can be found in the work of a Greek historian by the name of Theophrastus, who references Thales when writing in his work titled Physical Opinions. Quote, "Warmth lives in moisture. Moreover, the seeds as well as the nourishment of things are moist. And it is natural that what gives birth to a thing should also be its means of a nourishment. Since water is the first principle of the moistness of anything, they declare it to be the first principle of everything. Hence, they argue that the earth must rest upon water." Unquote. As we noted in our episode titled The Philosophical Atom, Thales is the first person we have record of who attributed natural events to natural causes rather than supernatural ones. In addition, Thales wrote that the earth itself was a sphere, the moon shone because it reflected the light of the sun, that solar eclipses were caused by the moon's shadow landing on the earth, and that lunar eclipses were caused by the moon somehow traveling through the earth's shadow. All correct suppositions. His thinking on eclipses and likely study of Babylonian eclipse records allowed him to predict that a solar eclipse would take place on May 28, 585 BCE. On this date, a battle between the armies of the Lydians and Medes was to have taken place, but the predicted eclipse threw the field of warfare into great confusion. This prediction cemented Thales' reputation as the preeminent philosopher of his day. Thales' student and colleague, Anaximander, had a somewhat different idea. Plutarch tells us that, quote, "Anaximander, an associate of Thales, said that the earth was cylindrical in shape, its depth being 1/3 its breadth. And he said at the beginning of the world there separated itself out from the eternal a something capable of producing heat and cold. It took the form of a flame, surrounding the air that surrounds the earth, like the bark of a tree. This sphere became broken into parts, each of which was a different circle, which is how the sun, moon, and stars were generated." Unquote. This idea of a great sphere, upon which were found the stars, sun, and moon, was a precursor to the idea of the celestial sphere we have discussed previously, something that will figure prominently in our story as we go forward. Another of Thales' contemporaries at the philosophical school at Miletus was one Anaximenes, who claimed, quote, "Air, when it condenses, becomes successively wind, cloud, water, mud, earth, and finally stone. In rarefying, it becomes ether, then pure fire." Unquote. Anaximenes also extended Anaximander's model, so to say that the sun and moon were disks on the hemispheres, suspended above the earth by borrowing from Thales. In his model, the moon was said to be a hemisphere 3 Earth diameters away from the Earth's surface, the sun 6, and the stars 9. At the rival philosophical school in Ephesus in Asia Minor, Heraclitus claimed that the primordial element was fire rather than water or air, and thought the sky consisted of a variety of bowls filled with flame. As the bowls turned, they revealed more or less of their generated light, an explanation for the phases of the moon and the various types of eclipses. According to the writings of Diogenes, the picture of Heraclitus said, quote, "Eclipses of the sun and moon occur when the bowls are turned upwards. The monthly phases of the moon take place when as its pole is gradually overturned. Day and night, months and seasons of the year are due to different exhalations." Unquote. In contrast to this, the philosopher Xenophanes held a different view. As reported by Hippolytus, Xenophanes said that things were assembled first from water and earth, as well as fire and ether. Quote, "The sun is formed anew each day out of small particles of fire joined together. He declared the earth to be without limit downward, as against the view that it is entirely supported by air or ether. An unlimited number of suns and moons exist, and all things come out of the earth." Unquote. As can be seen from these various pictures, there's a lot of diversity of thought regarding the nature of the universe here. There were, however, some common themes. First, the earth is at the center of each picture. In some cases it's a sphere, in some it's a disk, in others it's a cylinder, but in each model, the earth can be found in the middle of the universe. The second, in almost all of the models, one can find the use of either a sphere or hemisphere in some fashion to represent the heavens. Third, the universe is said to be constructed out of some basic substance or substances known as elements. While there was disagreement about what those substances were, each philosopher was clearly set on reducing the massive diversity of the natural world down to a much simpler picture. And fourth, the causes of change in these pictures, something especially important in the writings of Heraclitus, were not well explained. It was a philosopher from Sicily, that distant Greek colony off the boot of Italy, who would attempt to synthesize the parts of all of this. Empedocles of Acragas would be the one who would be there to say that there were four elements: earth, water, air, and fire, and that their combinations would make up all of that which we see. Moreover, he would attribute the cause of all of these changes, and hence all motions, to the driving action of strife and love, that would in turn divide and unify the elements. The ancient writer Theophrastus would say, quote, "Empedocles of Acragas considers the elements of things to be four, namely fire, air, water, and earth. They produce change, he says, by combining and separating. What sets them in motion is love and strife, alternatively bringing the one into union and the other dissolving them." Unquote. In addition to this, Empedocles would also construct an elaborate geocentric model of the universe. In it, a spherical earth was surrounded by stars made of fire and air that filled a second, greater sphere. In this sphere, the planets, including the sun and moon, were solid objects that moved through the space of the sphere while reflecting the light of the stars. Both the later Greek writers Aetius and Plutarch would write, quote, "The sky," he said, "is formed by air, being congealed by fire into crystalline form, and it embraces whatever is of the nature of fire or of air on either of the earth's hemispheres. Empedocles regards the moon as a mass of air congealed in the same way as hail and contained within a sphere of fire." Unquote. In his model, Empedocles seems to be drawing on the work of another earlier man who we have thus far neglected to mention. To be honest, I'm not exactly sure what to call Pythagoras of Samos. To some, he was a philosopher, to others, a mathematician. Still others regarded him as a religious or mythical figure. The best description of him is that he seems to have been all three, with his foundational mindset being rooted in seeing mathematics as expressing the underlying truth of the universe. As a result, the various symmetries of numbers and figures are both worthy of worship and the underlying a priori structure of the physical world. For Pythagoras and those who followed him, mathematics expressed the true nature of reality. To them, integer numbers were the most pure, and it was their ratios that gave rise to harmonious music on a string instrument. A 2-to-1 length ratio on a string was an octave giving the same note. A musical fifth was a 3-to-2 ratio, while a fourth was a ratio of 4-to-3. In music, the playing of instruments tuned to these ratios was thought by the Pythagoreans to restore and balance the soul. For a harmonious cosmos, The motions of the planets must therefore also be based on paths laid out according to these same ratios. Over time, these ideas would be developed to suggest that the universe was structured so that the motions of the planets would produce a sound that those possessing both a certain calmness of spirit and sufficiently sensitive and delicate hearing would be able to perceive. This would later be known as the music of the spheres, an idea that would inspire many a medieval and Renaissance astronomer, most notably a young Johannes Kepler. In addition to this work, the Pythagoreans put forward their own models of the universe. The most important attribute of these, historically, is that they were the first to put each planet on a circular path, each in some harmonic ratio with one or more of the others. One of Pythagoras' students, a man by the name of Philolaus, created a system wherein the Earth was not at the center of the universe. Instead, he claimed that the Earth orbited something known as a central fire, as did the Sun. Additionally, in the same orbit as the Earth was a counter-Earth that was always opposite the Earth from the central fire. When added to the 7 planets and the stars, this made for 10 objects that orbited the center. It is likely from the work of the Pythagoreans that Empedocles took his emphasis on a circular/spherical cosmos, something that would become an integral part of all Greek cosmological thinking afterwards. This would be reinforced by the writings of Plato and his emphasis on a world of perfect forms. As Brian E. Penpraise writes in his book, The Power of the Stars, How Celestial Observations Shape Civilization, quote, "The pre-Socratics each invented some of the ingredients of Aristotle's cosmology. Pythagoras brought the notion of perfect eternal circular motion as being the only appropriate motions for the celestial objects. Empedocles brought the notion of fundamental elements of nature, earth, air, fire, and water." Unquote. When combined by Plato, a specific type of cosmological model resulted, something called the two spheres model. Before we talk about that in some detail, let me make a few more comments about Plato. I discussed Plato's natural philosophy in some detail in our episode titled The Athenian Response, so let me summarize the relevant points here. Plato was what we now call a rationalist. He believed that our senses were unreliable sources of information for learning about the true nature of reality. Additionally, he thought that the reality we do experience is a somewhat crude and imperfect representation of a higher realm of forms, a realm governed by the mathematics of the Pythagoreans and others. Because of this, he felt that while things on earth might be flawed or merely shadows of the true reality of the realm of forms, he also saw that the heavens would more accurately represent this realm in their composition and motions. The most important aspect of this was the expectation that the heavens would follow immutable natural laws. It is here that we see the greatest difference between the Greek thinkers and their Babylonian contemporaries. The Babylonian astronomers, fundamentally empirical in their approach to their craft, were deeply involved in the nitty-gritty of making astronomical observations. While they did use mathematics, often rather advanced mathematics at that, it was to make predictions of where things would be or how long a day in the future might last. There was no evidence that they attempted to develop a cosmological model based on naturalistic explanations of any sort. While the planets might move in somewhat regular patterns, this was a reflection of the will of Marduk. It was the job of the astronomer to try to divine this will by examining those motions and predict them into the future so as to understand what the will of the gods would lead to. The Greek philosophers, on the other hand, rejected that the planets moved according to specifically directed wills of the gods. While Uranus or Kronos or Zeus might have established a structure for the universe as well as the dynamos or energy to initially impel it along its course, the planets now obeyed natural laws in their motions. Thus, the Greek mind, if such a thing can be said to exist, turned to attempting to understand the natural laws in order to explain the motions. If a natural philosopher could build an accurate model or description of the laws that govern the cosmos, he would be able to fully understand its behavior without needing centuries worth of data. would not matter if the model was mathematical, as would be the case with Plato and his student Eudoxus, or physical, as was held by Aristotle and later Ptolemy. The important thing was that there would be a model. So, to return to Plato, his model was based on the idea that there were two spheres, the sphere of the earth and the celestial sphere. That the earth was spherical was pretty well understood by the time of Plato, based on several pieces of observational evidence. In a supplement to this episode, we'll take a look at those lines of evidence, along with a few later pieces of work devoted to measuring the size of the sphere of the earth. So, for now, let's go with the validity of Plato's claim in this respect. There are a couple of things that should be noted about the model. First, the earth is at the center of the model, something we'll refer to as geocentric going forward. Second, in this model, the earth is said to be completely stationary, i.e., it doesn't move in any way. It doesn't travel through space, but more importantly, it doesn't rotate. We'll discuss the reasons for these assumptions when you get to Aristotle's physics. For the case of the celestial sphere, such a thing, turning on its axis around a stationary earth, would clearly explain the nightly motion of the stars. As a way of describing the celestial sphere, there are two things to mention at this point. First, it was a much, much larger sphere than the sphere of the earth, which could be thought of as something like the head of a pin inside of a very large balloon. This picture, however, gets to a conundrum that illustrates the second attribute of the sphere. In the picture I've just given, the celestial sphere is a physical thing, i.e., a balloon. However, from his writings, it's not clear whether Plato thought of it in this way or, if like we have done, he just used a physical thing as a method of illustration. Given Plato's penchant for mathematics as a pure description of forms, an argument could be made that Plato saw the celestial sphere as a mathematical object, a common distance from a center at which all the stars would be held in their common motion around an axis. For the planets, from the more regular motions of the sun and moon to the erratic retrograde motion of the more minor lights, similar circles or spheres were also proposed. However, while such a picture might work somewhat well for some aspects of the motion, they failed to accurately predict even the simplest true motions of the moon, much less that of the looping back and forth motion of objects like Mars or Jupiter. This irregularity seems to have concerned Plato quite a bit because the seemingly haphazard paths of the planets called into question whether there were actually natural laws that could be said to describe their motion. Because of this, he issued the challenge to his students and associates to see if someone could come up with the refined model that would account for the irregularities of the wanderers. The man who seems to have first stepped up was a mathematician and natural philosopher by the name of Eudoxus of Callipus. In my research, I've seen him referred to as one of Plato's students, but as he didn't live in Athens but only visited there on a couple of occasions, this seems rather unlikely. Perhaps a more apt description is that he was a visiting scholar, perhaps a bit like today's postdoctoral fellow to Plato's academy, younger than the school's founder, but adept enough to participate in the inquiry that took place there, even as he studied Plato's ideas. Unfortunately, none of Eudoxus's writings survive, so we are left with the references to his work in the writings of Aristotle, Hipparchus, that 6th century CE writer by the name of Simplicius that I mentioned in the introduction, and, of course, in the phenomena of Erastus, who seems to have used Eudoxus' work of the same name as the primary inspiration for his literary writing. The majority of Eudoxus' ideas on planetary motions, however, seem to have been contained in a work known by the title On Speed. Like Plato and so many others, Eudoxus was committed to the idea that the motions of the heavens, as accurate representations of the realm of forms, must be constructed out of the rotation of spheres. Hence, he set out to work out the motions of the two easiest planets to model, the sun and the moon, as combinations of the rotations of multiple spheres. To do this, he needs to make a set of assumptions about the construction of the universe that will be important to our conversation as we move forward. Let me quote these from the writings of Dr. Henry Mendel of California State University at Los Angeles. Quote, The first to present a general geometrical model of the celestial motion, Eudoxus started with 5 basic principles. 1. The Earth is the center of the universe. 2. All celestial motion is circular. 3. All celestial motion is regular. 4. The center of the path of any celestial motion is the same as the center of its motion. 5. The center of all celestial motion is the center of the universe. Since the apparent motion of all celestial bodies is neither circular nor regular, though it is to be about the earth, Eudoxus needed to construct models that preserve the 5 principles and the appearances. This means constructing the apparent motions as combinations of circular motions, the basic idea behind most subsequent Greek mathematical astronomy. And this leads to the 6th principle. The apparent irregular and non-circular motions of celestial bodies is a result of the combinations of real circular motions that satisfy principles 1 through 5. In other words, the models must preserve or save the phenomena. The model that Eudoxus produces to satisfy principles 1 through 5 has each motion being physically the rotation of a celestial sphere. The fixed stars, planets, sun and moon, as we see them, may be thought of as knots or pimples that occur on some of the celestial spheres. This leads to a 7th and 8th principle. 7. Each circular celestial motion is physically the motion of a single body. 8. Each individual body producing a circular motion is a sphere that rotates about a pair of poles." Unquote. In the case of the moon, Eudoxus said that the motion could be described by 3 separate spheres. The way to think of these would be to imagine the 3 as being closely nested, one within another, a bit like Russian nesting dolls. The largest of the spheres was that of what we've been calling the celestial sphere, and it turned on an axis aligned with the North Pole of the Earth once every 24 hours. Attached to this was a second, slightly smaller sphere that also turned on its own axis. This axis, however, was tilted by 23.5 degrees, which aligned the second sphere's equator with the ecliptic on the big celestial sphere. This second sphere turned at a rate of once every 27.3 days and accounted for the sidereal month length. The third sphere's axis was attached to the second sphere and was tilted from it by 5.2 degrees. The moon was thought to be attached to a point on this third sphere's equator, rotating with it once every 18.5 years. This is what accounted for the fact that there weren't lunar eclipses every month, but rather they occurred about every 6 months in different zodiacal constellations. So, using this, Eudoxus could describe the moon's motion through the sky by 3 attached spheres, each inclined to the other and turning at different rates. It's simultaneously pretty complicated and a pretty impressive intellectual accomplishment. A similar 3-sphere arrangement was constructed to produce the motion of the sun. For the minor planets, a 4-sphere construction was needed. The outermost 2 served a similar function to the outer spheres of the sun and the moon, while the inner 2 were responsible for producing a figure 8 motion that Simplicius will call a hippopede or horse fetter, after the tool used to allow horses to walk while tethered to a post. This figure 8 pattern would be carried along by the motion of the outer 2 spheres and thus would produce a type of retrograde motion. Now, before we go any further, let me say that it would be next to impossible to explain precisely how the motion of the 4 different spheres would combine to produce the motion of one of the minor planets, including that retrograde motion we observe, here in a podcast format. As you're probably already thinking as I try to work through the simplified description, this is just all way too complicated. So given this, there are 2 things we can do. One is to accept that Eudoxus's many spheres approach does produce a back and forth retrograde motion similar to what is seen, and we'll move on to the analysis here in a moment. The other is for you to go out to our website, thescientificodyssey.typepad.com, and I'll link there to a web page that includes a number of animations that will demonstrate how the multiple spheres moving together can produce the motion that Eudoxus describes. So, What's the upshot of Eudoxus's model? First, it allows or it shows that there's a possible way to address Plato's concern that planetary motions can't be produced by the regular motion of mathematical forms, namely spheres. While the motions of the model are only crude approximations of the minor planets, they did show that explanations using natural laws were in fact possible, something that was good enough to allay Plato's concerns. Second, it really does cement the ideas of uniformly turning spherical models into the Greek mind. This will remain the dominant structure of thinking in cosmology for the next 2,000 years. Additionally, some have claimed that it also cements a geocentric preference, but as we'll show, astronomers in the Hellenistic period will not be as wedded to that idea as is often portrayed. The problem with Eudoxus's model is it didn't explain two things very well. The first was the irregularity of the motions of the minor planets. In real observations, something Eudoxus probably didn't have very many of, as Babylonian data hadn't really started filtering into the Greek intellectual sphere yet. The retrograde motion of a given planet, say Jupiter, was different each time it occurred. Sometimes there was a looping path, sometimes there was a zigzag path. Sometimes the loop or zigzag was to the north of the ecliptic, sometimes it was to the south. Eudoxus's spheres produced the exact same path every single time. The bigger issue, though, was that the model couldn't explain the variations of the brightness of the minor planets, especially Venus and Mars. For example, it was clear to any careful observer that as Mars approached opposition, it became a lot brighter in the nighttime sky. In Eudoxus's model, the brightness of the minor planets should never have changed. In time, these failures will send Hellenistic astronomers in search of other explanations. In short term, however, Eudoxus's model, known as the homocentric spherical model, was a pretty major step forward, even as it was very, very complicated. The picture he proposed required 26 separate spheres to account for the motions of the 7 planets and the stars. This model was modified somewhat by a colleague of Eudoxus's known as Callipus, who increased the number of spheres, though I've had a hard time tracking down the exact amount. Some of my sources say that he only added 7 additional spheres, while others have him more than doubling the number to 55. If the former is the case, then it was Aristotle who increased the total to a rather mind-boggling level of complexity. In either case, the additional spheres were added as a way to isolate the spheres of one planet, say Jupiter, from being influenced by the rotation of the spheres of another planet, say Saturn. What is clear, however, is that by the time Aristotle is writing about the cosmos in his work On the Heavens, or De Caelo, as the work is known by its Latin name during medieval times, there is a well-defined model of the cosmos that is clearly enunciated. Beyond that, there will also be an entire description of the causes of motion that will seek to bolster and support this model. After the musical break, we'll take a look at the intertwined physics and cosmology of the greatest mind the Greek intellectual tradition produced, one that will weigh heavily in Western thought for the next 1900 years. The man who picks up the tapestry and adds the next thread is Aristotle, who we've already mentioned but deserves a more proper introduction. He was born in 384 BCE in a small town in northern Greece to a man who was the physician to the king of Macedon, Amyntas. At the age of 18, he enrolled in Plato's academy to study philosophy, and he would remain there for the next 20 years until he left over a dispute as to who would run the school following the great teacher's death. For a time, he traveled through the various islands of Greece, studying botany and getting married, until he was invited to the court of Philip II of Macedon to tutor the king's son, the famed Alexander. 8 years later, he returned to Athens to found his own philosophical school, the Lyceum, where he would remain for 12 years until he was forced to flee due to anti-Macedonian sentiments after the death of Alexander. It is during this 12-year period that it is thought that Aristotle composed most of his great works. For our purposes, the two pieces of writing that are most relevant are On the Heavens and Physics. In these, Aristotle not only lays out his version of the cosmos, but also sets forth a description of the causes of motion that support a number of the assumptions made in that picture. So let's begin by trying to set out and understand how Aristotle thinks the cosmos is put together. For him, the cosmos is divided into two realms, one terrestrial and one celestial. The terrestrial realm consists of a stationary Earth at the center of the cosmos and extends to a point just below the lunar spheres of Eudoxus's modified model. This is the region of change where the four elements of Empedocles combine and separate to form all of the substances we encounter. This process explains the growth and decay evident in everyday experience. Each of these elements has its own place, with the heaviest element, Earth, occupying the center of the sphere, water resting on top of that, air residing in the space above water, and then fire ascending to the outermost region of the terrestrial realm. Aristotle said that the motions of the objects of the sublunary sphere are in naturally straight lines towards or away from the center of the Earth, according to laws we'll discuss shortly. Above the terrestrial spheres, beginning with the spheres of the moon, is the celestial realm. In the celestial realm, there is to be found none of the elements of terrestrial experience, but rather all things consist of a fifth element, alternatively known as quintessence, literally the fifth essence, or ether, from a combination of Greek words for always runs. Unlike things here on Earth, the realm of the celestial is unchanging and eternal, and so objects in this region no longer have a natural motion of straight lines, but instead travel in unending circles, which allow for motion without change. One of the most fundamental places Aristotle diverges from his predecessors in this model of the heavens is that his spheres are real things. While it is hard to tell from his writings if Plato thought that the spheres he employed were just mathematical constructs, such a view would line up with his other writings that suggested that the best path to true knowledge was a rational consideration of the realm of forms. Eudoxus, at least as near as we can tell from the fragments of his writing that we have preserved by other authors, seems to have considered his nested spheres model a mathematical construct only, as did Callipus. Aristotle, however, was deeply uncomfortable with the planets not having something to move them, what he would call a moving cause. As such, borrowing from the ideas of the Pythagoreans, he made the spheres crystalline and assigned a prime mover that was unmoved to provide the necessary means to start the motion of the spheres. This, then, comprises Aristotle's astronomy, his description of the forms and motions of the heavenly bodies. As mentioned in the quote from Geometer, there is still a need to justify the astronomy through a discussion of the causes of the forms in motion, i.e., the physics. In Aristotle's physics, there were two types of motion, natural and violent. In the celestial realm, as we've already said, there was only natural motion, and that was for the spheres to turn endlessly, without change, causing the planets to travel in the way that is observed from the unmoving Earth. This, by the way, is probably a good place to discuss why the Earth was placed at the center of the model and why it was thought to be unmoving. As we will discuss in our episode on Hellenistic astronomy, this isn't the conclusion all Greek philosophers will reach, but it is the one that will win out. While there are likely some sociological biases towards human beings placing themselves at the center of the universe, because, as Solzhenitsyn wrote, quote, "The universe has as many different centers as there are human beings in it," unquote. This conclusion was actually reached through considering the empirical evidence available to the Greek natural philosophers. The first argument for a stationary Earth addresses the claim that the daily motion of the sky, i.e., the stars rising on the eastern horizon and the setting then on the western horizon, is due to the Earth turning on its axis rather than a celestial sphere rotating. The counterclaim to this comes from the idea that once you have a sense of how big the Earth has to be, something beginning to be grappled with at the time of Aristotle, it becomes pretty clear that if the Earth were turning, anything on its surface would be traveling pretty fast. As some of my listeners who grew up with a record player or a turntable will likely recall, when you put something like a coin on a spinning record, once you get the record spinning at any sort of rate, the coin will slide off the record and go flying through the air. If the Earth were turning, it seems unlikely that we humans wouldn't do the exact same sort of thing. And before you say, but hey, won't gravity hold us down? You need to remember that the idea of gravity as a force that holds things to the Earth won't be invented or discovered, depending on your philosophical bent, for almost 2,000 years. The second claim that was made was that the Earth, like the rest of the planets, traveled around or orbited some point or object. The argument against this suggestion, as was the case in Philolaus's Pythagorean central fire, is that if the Earth were to do that, there would be two observable effects. First, the stars on the celestial sphere would change their positions somewhat with respect to each other. This is due to an idea known as parallax, which you can see or have demonstrated for you just using your finger. If you hold your finger in front of your eyes at arm's length, and then close one eye, you can see your finger at a certain position. If you then open that eye and close the other, the position of the finger will shift. It was thought that if the Earth moved around some other center, the stars of the celestial sphere would be observed to shift over the course of a year due to the different observing positions of the Earth at different times. A second argument was that if the Earth and the Sun both orbited that central fire, there would be shifts or changes in the equinoxes and the length of the days on the equinoxes. As neither of these effects were observed, the most logical conclusion was that the Earth had to be taken as to being the center of the universe. So, with these two arguments taken together, we are left with a stationary Earth at the center of the cosmos, not just because it lined up with Plato's philosophical preferences, but also because it made the most sense given the empirical evidence. Over the last century, there's been a lot of ink spilled to say that Aristotle and those who followed him during the classical age were somehow intellectually limited or dogmatic, and they rejected the more correct models of those who claimed that the Earth orbited the Sun out of some blind adherence to a philosophical or theological scheme. This, I think, is really rather unfair. Given the evidence of the time, a stationary Earth seems like the best explanation, with a moving Earth being the idea that would require extraordinary evidence to support. With this in mind, we can then move to Aristotle's description of the causes of motion in the terrestrial sphere. As we have said in describing the philosopher's cosmology, the natural motion of an object is to seek its place in the proper sphere depending on the specific combination of elements it was comprised of. Earthy things fell in straight lines towards the ground because that was their natural place. Were there only natural motions, the sublunary sphere would consist of 4 perfect shells. However, as can be observed all around us, there is a second, different class of motions known as violent motions. When an object is lifted or thrown upwards, for example, it experiences a violent motion that interrupts its natural tendency due to a force or action being applied to it to cause it to deviate in some way. Another example of violent motion might be if you placed a book on a tabletop and then pushed that book across the table with your hand. So let's take a moment to look at these motions and see if we can reconstruct the picture Aristotle created to explain them. The first motion is natural motion. When we drop 2 objects, we can observe them falling and develop a description of that. Let's say we drop a metal ball and a crumpled up piece of paper. Perhaps you can take a moment to locate those things and give it a try. We'll wait. Go ahead. Pause the podcast. Go do the experiment. See what you see. Okay, so hopefully you did that. What you'll see, of course, is that the metal ball will hit the ground first in that case. Aristotle said that the reason was that the metal ball had more weight and so it falls faster. The extra weight, he said, came from the fact that it possessed more earth than the paper ball did, and so it sought its natural place more aggressively, I guess is a way to put it. A second experiment you can do is to take two pennies and drop them in the same way, with the flat side parallel to the ground. But in this time, you drop one through the air and the other through a glass of water. Again, you might want to try this on your own before continuing with the podcast. If you do this, you'll see that the penny falling through the air falls faster than the penny falling through the glass of water. The final observation one can make is pushing that book across the table. Try it. Push the book with your hand for a short distance and then let go and observe what happens. While you're pushing, the book moves at a certain rate, but when you remove your hand, the book slows down and comes to a stop. Now, what will happen if you pushed harder? Again, if you can, give it a try before continuing the podcast. What I expect you saw is that the book moves at a greater rate until you release it, and then it slows down again. With these three observations, or observations like them anyway, that led Aristotle to create a simple model to describe the causes of motion. The rate of motion is what we call speed. What Aristotle said was that there was a pretty simple relationship between speed, force, and something he called resistance. In his description, the more force was applied to an object, the faster it would move, just like with the book. He also said that the more resistance something experienced, the slower it would move, just as is the case when you drop the penny in the glass of water. The water has more resistance than air, so the penny falls through it more slowly. Now, before we move on, I want to stress that it turns out that Aristotle is wrong in this model, but I don't think we should be too harsh in our assessment of him. When I teach physics to college sophomores, one of the things I do is I assess their ideas when they walk in the door to get a sense of how they think the world around them works. This is something that a number of my colleagues all over the world do as well. When we all do this, we find that over 95% of the students have almost the exact same picture as Aristotle did. His conclusions are, in some ways, the most natural thing in the world to arrive at if you don't have an ability to make careful and controlled measurements, something no one will think to do for almost another, 1900 years, for a whole variety of reasons we'll discuss as we go forward. It won't be until the work of Isaac Newton that we'll finally get all of this stuff sorted out. There are two other notes that we should make before we wrap up this part with Aristotle's physics. First, due to the importance of resistance in his description of motion, he rejects the possibility of there being a void or vacuum as we think of it now. For him, if there were a place where there was no resistance, things in that place would move infinitely fast, which of course is an impossibility. This is one of the things that will lead him to reject the atomism of Democritus. The second problem here, the second thing here that we should sort of consider, is that he doesn't have a very good explanation for the process of the book slowing down after it is given the push and then released. According to his model, the book should immediately come to a stop as soon as there is no force applied by the hand. He tries to account for the continued motion by saying there's some sort of pressure force or something coming from the air filling in behind the book, but the whole thing's rather unsatisfying. In time, others will come up with a variety of models to account for this, including something known as impetus, but the issue again won't be fully resolved until Newton. So, as we reach this natural concluding point, let us make an assessment of what we have in Aristotle. We have an astronomical model of the cosmos that accounts for the motions of objects in the heavens and a physics that explains those motions. For the first time in human history, astronomy and physics are in agreement in producing a model of the cosmos that is self-consistent and self-supporting. It's really a wonderful accomplishment of the human intellect. Unfortunately, it won't last very long. Just as Aristotle is bringing the cosmos together in one grand explanation, his one-time student is bringing much of the world together under his control through conquest. As Alexander the Great takes his Greek armies across first the eastern Mediterranean and then through Mesopotamia across to India, he will begin a process of cultural integration that will bear unexpected fruit in many areas. For the purpose of our discussion, that integration will bring the Babylonian tradition of detailed astronomical observation and the vast collection of data that has been accumulated into contact with the geometrically inclined Greek mind and the models it had produced. It will create an exchange of knowledge throughout the Eastern Mediterranean that will find a physical and institutional expression in one of the greatest libraries ever constructed. As a result of this, new knowledge will be gained, but at the cost of a schism between physics and astronomy that will last over 1,500 years. In our next 2 episodes, we'll look at the great accomplishments of Hellenistic astronomy in determining the size of the Earth and the creation of one of the greatest scientific works of antiquity by one Claudius Ptolemaeus. As always, thanks for taking the time to listen to the show. Be sure to check out the music of the Blue Dot Sessions at www.sessions.blue, and if you're enjoying what you're hearing, tell a friend or a colleague. Until next time, full sails on your journey.